What if the biggest lie we were told about farming isn't about seeds or soil, but about energy? We've been trained to believe that crops only grow from what we pour into the ground. But a century ago, scientists discovered a way to grow 300% more food, using nothing but the air itself. Modern agriculture is built on an assumption so familiar that it almost feels like common sense. Plants grow only from what we put into the soil. Fertilizers, chemicals, water, labor, and machinery are seen as the drivers of productivity. If crops struggle, the solution is simple: add more inputs, more nitrogen, more treatment, more intervention. This belief did not emerge by accident. Over the past century, industrial agriculture has trained farmers, researchers, and policymakers to see farming as a chemical process. Crops are viewed as systems that respond primarily to measurable substances. Soil tests, nutrient ratios, and yield charts dominate decision-making. And for a long time, this approach delivered results. But assumptions can become limitations when they go unchallenged. By focusing entirely on what enters the soil, modern farming may have narrowed its understanding of how plants actually grow. Plants do not exist only underground. They live in a complex environment that includes air, light, temperature, microorganisms, and forces that are not easily measured or sold. What's missing from the equation is energy. Sunlight is recognized as essential energy, but it is treated as the only one that matters. Other natural energies, subtle, invisible, and constant, are rarely discussed. Modern agriculture operates as if plants are isolated chemical factories rather than living organisms interacting with their surroundings. Yet biology tells a different story. Living systems are not just chemical, they are also responsive, adaptive, and dynamic. Animals rely on electrical signals for movement and communication. Human hearts and nervous systems are electrical by nature. Cells themselves operate through gradients and charges. So the ignored question becomes unavoidable. Is farming only chemical, or is it also energetic? If plants respond to energy in ways we have overlooked, then modern agriculture may be incomplete. Not incorrect, but partial. Like studying nutrition without acknowledging metabolism, or engineering without understanding physics. This question matters more now than ever. Rising fertilizer costs, soil degradation, and environmental pressure are forcing agriculture to rethink its dependence on constant inputs. If growth truly depends only on purchased materials, farming will always remain costly and fragile. But if plants also interact with natural energy already present in their environment, then agriculture may have overlooked a powerful variable, one that cannot be poured, patented, or easily controlled. And that possibility opens the door to a very different understanding of how plants grow. Every plant on Earth exists inside an electrical environment, whether we acknowledge it or not. This is not theory, it is established physics. The Earth's surface carries a negative electrical charge, while the atmosphere above it carries a positive charge. Between them exists a constant electrical tension, known as the atmospheric electric field. This field is always present. It does not require wires, generators, or human intervention. It exists day and night, across farms, forests, deserts, and oceans. It is part of the planet's natural system. Plants live directly inside this field. Their roots extend into the negatively charged soil, while their stems and leaves rise upward into the positively charged air. In simple terms, plants are naturally positioned between two electrical poles. They are not passive objects sitting in dirt. They are living structures interacting with their environment from the ground up. Despite this, modern agriculture almost never mentions electricity as part of plant growth. The atmosphere is discussed in terms of weather and climate, but rarely as an energetic space. Farming models focus on soil chemistry and ignore the electrical context plants evolved within for millions of years. That omission is striking. Electricity plays a fundamental role in life. Cells communicate through electrical signals. Biological processes rely on charge differences across membranes. Even microorganisms respond to subtle electrical changes in their environment. Plants are no exception. While they do not produce electricity like machines, They respond to electrical conditions in measurable ways. Growth direction, root behavior, and internal signaling are all influenced by electrical gradients. The atmosphere is not empty space. It is charged, dynamic, and active. Lightning is the most dramatic example, but it is not the only one. A constant, low-level flow of energy moves between earth and sky at all times. Plants, rooted below and reaching above, are uniquely positioned to interact with this energy. If that interaction matters, and evidence suggests it does, then agriculture has been overlooking a fundamental environmental factor. Not something artificial or added, but something natural and ever-present. Understanding this energy does not mean rejecting soil science or fertilizers. It means expanding the picture. It means acknowledging that plants grow within systems larger than the ground beneath them. And once that is acknowledged, the next question becomes inevitable. Can this natural energy be guided or supported in a way that benefits plant growth? History suggests that question was already asked and answered over a century ago. At the beginning of the 20th century, electricity was one of the most exciting scientific frontiers in the world. Researchers were uncovering invisible forces that shaped reality: magnetism, radio waves, electrical currents, and discovering that these forces had real, measurable effects. It was only natural that scientists began asking whether electricity influenced living organisms, including plants. Experiments soon followed. Across Europe and North America, engineers and botanists studied how electrical conditions affected plant behavior. They observed that roots responded to electrical gradients in soil. Seeds exposed to certain electrical environments germinated faster. Growth direction could be subtly influenced using weak electric fields. These findings were not dismissed or ignored. They were documented, discussed, and replicated. At the time, this research was considered legitimate science. Universities, agricultural institutions, and government bodies took part in the investigations. The results challenged a purely chemical view of plant growth. Plants were not just absorbing nutrients, they were responding to signals. Electrical conditions influenced how roots spread, how quickly seeds awakened, and how plants oriented themselves in their environment. This aligned with discoveries happening elsewhere in biology. Scientists were beginning to understand that life operates through communication systems, not just material exchange. Cells used electrical impulses. Nerves relied on voltage changes. Biological organization depended on gradients and fields. In that context, the idea that plants responded to electricity was not radical, it was logical. By the early 1900s, the conversation had shifted from "does electricity affect plants?" to "how can this knowledge be applied?" Could natural electrical forces be used to support agriculture? Could growth be enhanced without adding chemicals? These were serious questions asked by serious researchers. Among them was a French engineer who believed the answer was not only yes, but simple. Christofleau was not a farmer by trade. He was an engineer, trained to think in systems and structures. Living in early 20th century France, he was deeply interested in electricity and its role in nature. Christofleau believed modern agriculture was overlooking a natural resource that had always existed: atmospheric electricity. Instead of forcing plants to grow through chemical inputs, he proposed helping them interact more effectively with their natural electrical environment. His solution was remarkably simple. Christofleau installed wooden stakes in agricultural fields and ran thin copper wires upward from them, creating antenna-like structures above crops. These wires were not connected to batteries, generators, or any external power source. They used no electricity in the conventional sense. Instead, they interacted passively with the natural electrical charge of the atmosphere and directed it into the soil. The system had no moving parts and required no ongoing energy input. Christofleau called this method electroculture. The idea was not to shock plants or artificially stimulate them, but to enhance the natural electrical conditions they already lived in. Much like improving reception for a radio signal, electroculture aimed to help plants access energy already present in their environment. Christofleau patented his designs and demonstrated them publicly. Farmers were able to replicate the system easily, using inexpensive materials. The method required no specialized training and no continuous purchases. For a brief period, electroculture was viewed as a promising agricultural innovation. What followed would determine its fate. Reports from the 1920s described results that were difficult to ignore. Farms using electroculture systems experienced dramatic increases in productivity. In some cases, yields reportedly increased by as much as 300%. Vegetables grew larger than expected. Crops matured earlier. Plants displayed improved resistance to frost, pests, and disease. These effects were observed across different regions and crop types. Importantly, these results were not limited to a single demonstration. Farmers replicated them independently. Christofleu's methods were patented, and public trials were observed by officials and agricultural authorities. Electroculture appeared to work, and that success created a problem. The system required no recurring inputs. Copper wire and wooden stakes lasted for years. There was no fertilizer to repurchase, no chemical dependency, no supply chain to sustain. As industrial agriculture expanded, this became a critical flaw. The agricultural economy was shifting toward mass-produced inputs that could be sold season after season. Chemical fertilizers fit perfectly into this model. Electroculture did not. Its success offered no ongoing profit. That made it invisible to the systems that decide what gets funded, taught, and scaled. Electroculture did not disappear because it was disproven. There was no major scientific rejection, no public scandal, no decisive experiment that shut it down. It simply faded away. After the World War eras, chemical fertilizers flooded global markets. Industrial facilities designed for explosives were repurposed for agriculture. Nitrogen-based products transformed farming, offering fast and predictable yield increases. Research funding followed profit. Universities focused on chemical solutions. Governments invested in industrial-scale agriculture. Electroculture, which could not be easily monetized, fell outside these priorities. Without funding, research stopped. Without research, education stopped. Without education, memory faded. Electroculture wasn't attacked, it was abandoned. Modern plant science now confirms many ideas that early electroculture researchers observed. Plants generate internal electrical signals. Cells communicate through voltage differences. Roots respond to electric gradients in soil. Soil microbes, critical to plant health, are sensitive to electrical conditions. Electrical stimulation is actively studied in plant biology laboratories. The influence of electricity on plants is no longer controversial. What remains controversial is the idea that naturally occurring atmospheric electricity could play a meaningful role in agriculture without artificial power sources. The science has moved forward, but selectively. Electroculture has reappeared quietly outside institutions. Independent gardeners and small-scale farmers have begun experimenting with copper wire antennas near their crops. They report taller plants, thicker stems, and healthier growth, often with reduced fertilizer use. These experiments are informal and uncoordinated, yet similar outcomes appear across different climates. Dismissed as anecdotal, the results persist, and persistence raises questions. The deeper issue is not whether electroculture works perfectly, it is why it was never fully explored. Research follows profit, not curiosity. Ideas that cannot be owned or sold struggle to survive. Electroculture may not be a miracle, but it may be a missing layer of understanding. The uncomfortable truth is simple. We stopped asking, not because the question was answered, but because it no longer fit the system asking it.